Hey everybody, and welcome back to Linear Algebra Online. So today I want to just talk about sort of some non-standard conditional statements, like a biconditional, which is right here, and some proofs involving sets. So we actually work with sets quite a bit in linear algebra. There's a whole bunch of things where we're talking about like subspaces, and you'll see. But sets become a big part of our class, and it's important that we kind of know how to really just do, I guess, one particular part of proofs involving sets. And this video will basically be our last video for this little detour into proofs. There is actually one more really important technique called induction, but we're not going to talk about that quite yet because I want to motivate it with an example once we get to that. So don't worry about induction right now. Proving biconditional statements is basically just a problem where you get two problems of the price of one. So they're just statements where we write P, like some statement, right, if and only if Q. And it boils down to just two things we have to prove. So we have to prove like if P then Q, and we have to prove like if Q then P. Sometimes we write a little IFF if we're being lazy, and you might also see so this IFF stands for if and only if. Another thing you might see sometimes is someone does like P and then that kind of double arrow Q, and that's just there to say that there's like an implication going both ways. But basically we do run into these a lot, and it's important you kind of see an example of a proof with them. There's honestly a lot of our theorems are actually if and only if statements, so you'll always have to prove something in both directions in order to fully prove it. And I thought this was a good example. I just pulled this out of the book. So we're going to basically assume that A and B are just natural numbers, and then the statement is that if A equals the GCD of A and B, that happens if and only if A divides B, okay? And when you write these up, it's probably not like very professional, and I wouldn't do this if I was submitting it to like a journal, but when you write up like problem sets and things, it's kind of good to show the reader, like basically show the teacher which direction you're proving, and you should always state one proof in a paragraph, like one direction, and then do a new paragraph for the other one. So I'm going to start off with a little arrow in parentheses, and that's just my way to say I'm basically going to assume that A equals the GCD of AB and show that A divides B. And this one's really quick because we could just say, by definition, A equaling the GCD of AB implies A divides B, and I should really say A divides A. So, yeah, we're basically done. There's not much to say, right? We wanted A divides B, and we get it just basically straight from definition. It's just what it means to be a GCD. It's going to divide, right? So then, again, the super not professional thing to do, but I'm going to like start a new paragraph with an arrow going back, and then I'm going to start off my paragraph saying, I'm going to now assume that A divides B and show that A equals the GCD of AB, right? And really, like, this one's not so bad either. There's like a little bit more work here, so I'm going to start off, if A divides B, I'm going to also add the part here, let's keep this in blue. So I'm going to just add, I guess, a simple sentence. We know A divides A by definition, I guess. And A divides B. So we know that A is, I think I'm not going to have room there. I'm just going to say we know A is at least less than or equal to the GCD, right? It might not be the greatest common divisor, but if, everything divides itself, so that's the silly little A divides A I'm talking about, and we were given A divides B. So we know it's at least less than or equal to the GCD. And really the problem just becomes showing that it is the GCD. So we have that by definition, the GCD of AB would divide A. So basically we can say that like A equals the GCD of AB times like something like alpha for that alpha in like the integers. Now we basically just said that A, I guess this is where we should use note A is part of the naturals, so why is my eye not cooperating? I think I'm running out of paper here. So it follows that A would be greater than or equal to the GCD of AB. Now let me explain. This part's kind of weird. It's not, let me stress it this way, I guess. Actually, do a different color. All right. So we have this statement just by definition of divides. And we just said, since this is positive, this only works because this is positive. But you have the GCD of AB times something, right? So basically it had to have gotten bigger. Or it could get equal to it, which is really what's happening. But it basically, because we're multiplying two numbers, then this thing, and they're all positive, this thing should be greater than or equal to one part of it, right? Of the two factors there for A. So then we basically have it. Since A is simultaneously greater than or equal to the GCD of AB, and A is less than or equal to the GCD of AB, we know the only option is that A equals the GCD of AB. And that is what we wanted to show. Another style of proof that we're going to see this year are, and this one's actually really, really big, is equivalent statements. Theorems is what I'm calling them. This is actually out of your proofs book, but it's actually also in your linear algebra book. And I think this is technically the fundamental theorem of invertible matrices version 1. Ooh, that's the name. So this thing is very famous in linear algebra, and I know I showed you at one point the final version, which has like a bunch more equivalent statements coming down here. We basically spend the entire year of linear algebra just going through and learning different things that are the same. It's almost like a course where you're like, hey, 1 equals 2 divided by 2. It also equals 3 divided by 3. And guess what? 4 divided by 4, and so on. And all of these different little facts in here sound different, but they mean the same thing. And these are very, very useful theorems in math, because really the power of it is if one fails, they all fail. Or vice versa. I'm just just going to do it that way instead of vice versa. The idea being like, if, I don't know, take this. So if the determinant of the matrix actually equals 0, which is the negation of that, right? Then we could say that the matrix A is non-invertible, all right? And say you find out that the matrix A has a singular, or has 0 as an eigenvalue, then likewise you could be like, okay, well then the determinant has to be 0. It's either they're all true or they're all false. And in math, a lot of times we're just trying to categorize like different things. And if we can like find one fact, but then we have some result that tells us a whole bunch of other facts, it helps us a ton. So this is something that we're going to be working with a lot. And last time I taught this class, I actually did have them prove like the full, I think it's version 4 in your book or something like that. But basically the way you prove these is, this is like the simplest way. You sort of just make like a chain of implications. So you could start with A, and you can assume A is true, and then you could use A to prove B. And then if you assume B is true, then you use that to prove C, and then assume C, imply D, D imply E, E imply F. And the reason this is going to be fine is because of this last part now. So F is going to imply A, which if you think about it is like them creating that cyclic argument, and so all of them are going to be equivalent. And there's other ways to do it, and that's just what these two things over here are saying. You could, I don't know, like maybe you find F to A is really hard for you to prove. So you can actually prove a biconditional between A and B and E, and then F and E, and that still links F back to A, right? So as long as you figure out some system where you have like a chain like that, where all of them sort of still create a loop, and that can be done biconditionally like this, I guess more like this, then that's fine. So, this is another option that would be valid. You could do like a loop over here, but that would leave out C and D, so you have to show that C is actually an if and only if with B, and you have to show that D is an if and only if with E. So I typically would recommend you try to do this. It seems to be the least amount of work. Sometimes these ways can be like more work. Another non-standard conditional statement is something called existence and uniqueness. And these show up all the time in our class too. So this is actually a theorem out of your book. It doesn't necessarily mean much to you right now, but I'm still going to read it. So it says, if A is an invertible n-by-n matrix, then the system of linear equations given by Ax equals B, those are vectors right there, has the unique solution x equals A inverse B for any B in Rn. Okay? And it kind of hides the existence part, but this right here is basically stating that there exists a solution. And then it's saying the solution that we get is unique. And this is a very powerful result in math, to say that, hey, we know we can solve something, and when we solve it, there's only one option. This is a big thing actually in differential equations, which is what this comes from down here. I actually just went to a primary source journal and pulled out existence uniqueness theorem. These are kind of cool things if you ever want to talk about them. There's actually fractional derivatives in the world, and that's what this is doing. But this is a existence and uniqueness result or theorem that they go on to prove in this paper, relating to fractional order differential equations. So that's a thing. These are basically the initial conditions. Like if you think back to Calc BC, you have like that initial condition problem for differential equations. This does it for like an n-dimensional system, and the derivatives are not like 1, 2, 3 like that normal kind of way. They're actually fractional derivatives, which is a weird thing. That's what this alpha is. You can see it right there. and d is like the derivative there. So they show up in differential equations, they show up in linear algebra. This is like a number theory kind of problem, which I think is funny that this is in your book. But if you ever just have a there exists thing that you need to prove, they're really easy because you're like, oh, there exists an even prime number. You can be like, 2 is 1, and then you can just say, done. So if you want to show there exists, like prove that there exists, you just have to find one. That's the idea. Proving uniqueness is a lot harder. So we will kind of get into this some more when we get there, but there are some common tricks, but it is tough to... Okay, I don't know if you heard that, but someone came in my door and messed up my video a little bit, so if there was a weird noise, I'm not going to go back and edit it because I don't have time for that. But the point is, existence proofs are straightforward. Find one that works, and then you're done. And uniqueness is harder, and all I will say basically about that is, right down here, a common trick to prove these is to actually use proof by contradiction. And the reason that works is you can assume there exists like 2 solutions maybe, and arrive at a contradiction. I spelled that word wrong. It's okay. So for example, if I took this problem, so to show that there exists a unique natural number d that blah, blah, blah happens, a common way that we might try this is actually we would sort of assume there exists like d and, I don't know, e in the natural numbers such that blah, 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 blah. And then we would arrive at hopefully some sort of contradiction in here when we're assuming that 2 things do it. And then the idea is like, well, if we can't have 2 things do it, then there must actually only be 1. This is actually a really good problem because it's got existence, uniqueness, and an if and only if. So it's kind of long, but it's a good one to read. It's on page 153 in the book. So I would recommend you go just try to read that. I mean, this isn't a number theory class, so I'm not going to like really test you on these per se, but this is still a good example of like the kind of proofs that we're going to do. All right, so on to the last chapter in this little detour. So proofs involving sets. What we really need from this chapter is to figure out how to prove A weird symbol B, B weird symbol A, and A equals B. And A and B here are sets. So sets, again, just being like collections of objects or things. You know, it could literally be like A could represent the amount of houses in a neighborhood, or it could represent like the amount of Mersenne primes below 16 trillion or something like that. And this symbol, if you don't know it, is what we call subset symbol. And the subset symbol is pretty self-explanatory. Basically, it means that this set is fully contained in this set. And what we need in linear algebra is to be able to show that certain things can be vectors, it can be entire spaces, are contained in other things. And the way we show 2 sets are equal is actually very much related to this, which is why these really are all connected. And not that like we need a lot of this stuff down here, but just so for the sake of examples, I wanted to kind of pull these definitions out from the beginning of that proof book. So if you go into math, or I would say mostly just math, honestly, you're going to study sets a lot more. And I could talk about this for literally ever, but I'm going to keep it really simple. So there's something called a power set, and it's literally the set of all subsets for that set A. So it's like the brackets denote the set, and then we're saying it's the set of all x's such that x is a subset of A. And I'm going to actually show you an example of this. We use this weird little script P for it. These are three other big ones that I just think you should kind of see if we're talking about sets. There's something called union, which is basically like your disjunction, your V. Then there's something called intersection, which is basically like, maybe I should write, this is your disjunction. Disjunction is basically the logic form of this operator. Intersection, we use a weird kind of upside down U. So the U is for union, and then the intersection symbol is kind of like an N, but there's no little vertical part over here. But that symbol is kind of like the V, like the caret symbol, which is the conjunction one, right, from logic. And the last thing here is actually exactly like what we usually write for logic. We do a subtraction sign, and that means difference is what we call it. But basically, if you're in a union, you're in A or B. If you're in a intersection, then you're specifically in the overlap between the two. So this one doesn't have to be overlap. You can be specifically just in A or just in B, and then you'd still be in the union. This gives you bigger sets. This gives you smaller sets, the intersection. And the difference is basically you're in the A but not in the B. So you take out the B elements from A. That's the idea here. So what I really want to just do is get to a point where I can show you how to prove actually that two sets are equal. And I'm going to do it with a power set problem. And to start off, I just want to show you how we work with power sets, basically. And I realize I don't really want this here yet, so ignore that right now. So if you have these two sets, and I wanted to find the power set of A, it would literally just be the set of all subsets. So the empty set is a subset. Then you could have a set with just one, just two. Just two. So those are, subsets of this set 1, 2. Then you could have the full set. Everything is a subset of itself. So that would be the set of all subsets for A. And then the power set of B would be, again, the empty set's always a subset. Then you could have 2, you could have 3, and you would have 2, 3, the full thing. This last one too, you could also write, because it's defined as B, you could put B there if you want. This one you could also put just A. All right, so I want to prove this. So I want to show that if you combine the elements from the power set of A with the power set of B, then that stuff is contained in the power set of A union B. So if you union them first, and just to be clear, A union B would be the set 1, 2, 3. You just combine the elements. So if you took the power set of this should be bigger, basically, have more stuff in it, and than this one. This one should be fully contained in that one. So the way we prove these kind of containment things is we're basically going to just let something called X be in the power set of A union power set of B. And I'm going to show that X is in the power set of A union B. And the idea is as long as that thing X you pick is very general and you follow this through, then anything in here shows up in here. So this set is contained in that set. That's the idea. So if you just follow the definition of union. I'm going to say X in the power set of A union power set B implies that X is in A or X is in B. So now I'm going to just do like some cases. Case 1 is going to be X and A. And for this case, then X is part of the set A union B, right? Because if you're in A, you're in A union B. So X would be in the power set of A union B, right? Then if you do like case 2 or something, now X in B, then X is contained in A union B, right? So now it's like you should be thinking you're from this set, but you're still in the union instead of this set. That's how you got in there before. So for the same exact reasons, it's in the power set of A union B. So either way, you're in there. So X must be in the power set of A union B. And that would basically prove it, actually. That's all you have to do. And this is where I wanted to talk about this. So to show, what we're going to often have to do is show that two sets in linear algebra are the same thing. And what you basically have to do is kind of go through this, but in both directions. It's almost like a biconditional set containment proof. So you're going to pick, if you want to show like two sets are equal, you pick something in A, arbitrary thing in A, and show it pops up in B. And then if you want to show B is contained in A, then you pick an arbitrary thing in B, and you show it pops up in A. And the idea is like, the only way A can be contained in B and B can be contained in A is if they're actually equal. It's kind of like that GCD problem where it's like, if A is less than or equal to B, and you have that B is less than or equal to A, then you better have that A is B. There have to be this. It's the only way that and can cooperate with those two things, right? And we'll definitely review some of this when we get to them, but this is the general idea. Pick something in one set, show it pops up in the other. And there's so much more to say, but about sets, it kind of feels weird to just talk about it for 2 seconds here, but we will need this result at least, being able to prove two sets are equal. One last thing I just wanted to define with sets that kind of isn't necessarily related to that proof or anything, but just another operation you can do with sets, is something called like the Cartesian product. So this is the definition. You can find it near the front of the book, but it's almost easiest to show what it's doing in a picture. So if you have 1, 2, 3, and then you have negative 1, 0, 1, the Cartesian product of these two basically just forms an ordered pair that would be these 9 points. You can do this with like sets like that are infinite too. Like there's an example in the book like this. But you can do one that you definitely know. If you do actually R cross R, that literally is just your full number lines crossed together. And that's what we write as R2. If you take a look at like a lot of our theorems this semester, you'll see them written as Cn, and that's basically just C cross C cross C, blah, 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 for however many times n is. And it's basically a n-dimensional complex hyperspace is the idea. But that actually is a formal definition that comes out of sets. So I thought I should just show you one of those because we'll actually see this a lot this year too.